I already start recording. We stopped here last time. We're still talking about chapter 15, which is a bulk metal deformation. Chapter 15 is a bulk metal deformation, and bulk metal deformation is four items: rolling, forging, extrusion, and wire rubber drawing. We're still talking about rolling. First one, which is rolling. Already we started last time. We continue talking about the rolling process. In rolling, not only we reducing the cross section, but also shaping the cross section. Not only reducing, but also shaping. Can you see that there are a shaping here? We're shaping the cross section, as you can see, by using the accomplished by the passing through a roller that have reverse desired shape. So roller have the reverse desired shape. Then when a bar pass through the series, not combination of rollers. Combination of roller had the opposite or reverse desired shape. So when it passed through, it will be shaped as you can see here. Different shape can be done by the rolling. So this is whatever we call shaping, cross-section shaping. Production is I-beam. This is the I-beam. This is different type of I-beam, C-channel, angles, railroad. For strain and round a square bar and so on can be shaped by rolling as well. Different shape here. This you can see. This is different shape done by rolling. So all done by rolling process. So rolling can save this kind of cross section. Actually, when you see it is series of roller, it is not only one roller, but it is series of rollers at different stages to finally perform the required cross section. So you can see that here. It is initially sheet. This one is the first stage, the sheet. Second stage, you do a little deformation. Fourth stage or third stage, you do more deformation. Fourth stage, you do more deformation, and finally, you can perform the required cross section. This is the stages. This is stage 1, stage 2, 3, 4, 5, and then here you can see that. So initially start as a flat, but at the end you get the desired shape at the end of stage. So it is series of roller. Actually, it should be designed. The series of rollers should be designed to finally get whatever you would like to have. It is a series of rollers, then you can shape the cross section. So this is another 3D view of series of rollers. As you can see, one roller, a second series of roller, and so on, combination of roller, and finally you can obtain same here also. Initially sheet, as you can see, initially sheet. Then you deform, finally you can obtain the required cross section. So you start with sheet, and then finally you can deform based on it. May be sheet, sometime not sheet. Here, for example, not sheet. So here is the bulk deformation. Then here it is bulk plume. Then we use here is initially plume, which is rectangular shape or something, and then finally you obtain the desired shape. So it is series of roller should be designed to finally get whatever desired cross section or desired shape cross section. As you can see, this is the actual photo to show you it is series of rollers. So how many? It is many. You start with something here, then you just at the end of the line you get the final desired shape. So it is series of roller being used to get whatever desired shape. Okay, let me show you this this video. Let me share. Okay, not yet come. Finally come. Okay, so let me just show again. This is the bloom you put here. Can you see that? Series. So you get one stage, another deformation, more deformation, and then you can just go through a third stage, for example. More deformation you obtain, and then another deformation. Then another deformation. You see that the shaping, every section do more deformation, and finally desired shape can be obtained in the final stage. Actually, in many cases, they don't put in this way, they put as a series in parallel, not just in series. So this is usually series of deformation, and finally can obtain whatever process could be done. Okay, so get back to slide again. So series of deformation and finally get the shape right. We have whatever we call equipment in a rolling usually is expensive, and we have certain configuration in a rolling. We have some configuration. We call it is a 2 height mill, 3 height mill, 2 height mill, 3 height mill, 4 height mill, cluster mill, and tandem rolling mill. This is a configuration in rolling process. Let me show you the configuration in the rolling process. This is a 2 height. 2 height mean the 2 roll, 2 opposite roll. This is the one. 2 opposite rolls, they call it is a 2 height, right? This is the 2 height opposite to reduce the cross section or to deform and so on. This is the 2 opposite roll. 3 height is this one. This is the 3 height. This is the 2 height, and this is another stage. Then a workpiece will move in the first stage and then come back again to the next stage or second stage to reduce more. The workpiece pass through roll in both direction, one direction and then another direction. This is whatever we call 3 height. 4 height, actually, this is a 4 height. If you look to the 4 height, you find that 4 height actually used in supporting to support the small roller. Then we call it the backing roll support small roller. This is a small roller here, and this is a back supporting small roller. Because if no supporting, this is small roller here. R here is radius, A is small. Someone said that why small roller. Actually, most precise rolling is small roller. So L equal to square root RD. R radius and D draft. D is a draft and R is the radius of the roll. Then L here, whenever L is reduced, the force is reduced, then precisely you can just accurately get. So precise roller or precise rolling process done as a small roller. This is the way to reduce the power and force and so on. However, small roller is weak. I mean, can be bent or can be deformed easily. You can see that this is a way active. This is exaggerating just to let you know, to just excuse me, محمد ايه المشكلة؟ محمد بيقول there are some voice that come from your mic.
خشخشة زي خشخشة مع صوتك نفس الوقت.
كل الناس كده يا شباب؟ نفس الكلام عندكم؟
صوت هواء خفيف دكتور، يعني ما هو اللي
صوت هواء خفيف؟ واضح ان حد فاتح المايك، بيتهيألي مش من عندي.
من المايك لما تحرك المايك حقك دكتور ممكن.
طيب كده لسه موجود ولا خلاص؟ طب انا هقفل المايك عندي كده وشوف الصوت ده موجود ولا لا. انا هقفل
كده راح يا دكتور.
الصوت راح. انا فتحت المايك تاني، الصوت راح لما قفلته؟
الحين
ايوه راح لما قفلت.
كده كويس دلوقتي؟ سامعني كويس كده؟
ايه كده تمام.
طيب تمام. نرجع تاني للفور هايت. 4 هايت يا شباب، يعني الحقيقه الاثنين دول بيعملوا سبورتنج لسمول رولر. سمول رولر لما نقول سمول رولر mean the radius is small, mean this one become weak, then probably it deformed as you can see here. This is very exaggerated. It is in a micro scale. Even deformation in a micro scale, not big deformation like this, but we need precise rolling. Then we have to maintain the dimension accuracy as the best. So in this case, they providing these two roller to support the small roller here. So they call four height roll. This is a four height roll, as you can see. So packing roll supporting small roller. This is a four height. Next is whatever cluster mill. Cluster mill is same, very similar to the four height, but more than two roller to support a small roller. So you can see that there are a cluster, we call cluster mill. This is actual photo. This is a multiple packing roll in a small roller. You see, this is a roller in rolling process. This is actual photo, and this is a small roller. This is a roller to do the rolling process. Sheet is coming here, and this is a roller to do the rolling process. Whatever else is just supporting. So you see that this is a small roller, another support, another supporting support, another supporting support to precisely get. So there are no way, or there are no any chance for any deformation. Many rolls supporting the small roller here, as you can see. So we call multiple packing roll, we call cluster mill. Finally, we have whatever we call tandem rolling mill. Tandem rolling mill is the two height series of two height. This is the two height, another two height, another two height. Here you reduce some section and deform. Here another reduction and deformation. Here another reduction and deformation, and finally you obtain the desired shape or cross section. Right. So this is the configuration. Other deformation process related to the rolling, other deformation processes related to the rolling process, we call ring rolling, thread rolling, gear rolling, roll piercing. Let's take one by one. This is the ring rolling. Ring rolling to create ring. To create ring, actually you start with a thick ring here, as you can see, thick ring here with a small diameter, thick ring with a small diameter, and then you apply rolling process. There are a series of roller here, and these two roller approaching get small here, small dimensions. Then you reduce the thickness and expand the diameter. So you reduce the thickness and expand the diameter to create a ring by rolling process. You reduce the thickness it will be reduced, and diameter will be expanded to create a ring. So we call it the ring rolling process. So large ring being used for rocket, turbines, gear wheel, rim, and so on. I mean, this is for several applications. So this ring could be taken and deformed and somehow for several applications. So we call it a ring rolling operation. This is the first one. This is a ring being obtained. This is a ring being used to create several deformation for several applications. This one produced by rolling process. Next, we have whatever we call gear rolling operation. Gear rolling operation. Actually, the final desired shape is gear. We would like to manufacturing the gear, this gear at the end of process. So we manufacturing gear at the end of process. So how to manufacturing gear actually? You get a blank here. Blank means this is a workpiece. Blank, there are no any teeth here, as you can see. So it's blank. And this blank you put between the two, roller. This is the roller, two roller. This roller, we manufacturing the teeth on the peripheral of the roller. As you can see, this is one roller. This is another roller. They are rotating and approaching as well. So moving in radial direction. So they copy the the teeth profile in the here, in the gear, or in the workpiece. Then finally you can produce, with the rolling process, you can produce gear. So this actually is a fast way and easy and cheap way to manufacturing gear, very fast. This is a production rate manufacturing. Other technique is to use a machine, milling machine. We can use the milling machine to manufacturing gear, but it takes time. Shorter time is done by the rolling process. So gear can be opened by using rolling process. In very similar way, like gear, also we can open or manufacturing the thread. So we call it thread rolling. Thread rolling, this is the two flat plate, or this is a two method actually to make thread, which is flat die, and this is a circular die. This is circular die, this is a flat die. Circular die, if you put between the circular die, flat die, if this one are moving, they are moving against each other. Start with a blank. This is a blank, you put blank here, and this one moving. You create the thread profile in the die. This thread profile here and here. You put the blank here. This is a blank. Blank mean is a new one. And then you move this one, they move against each other. Then finally, at the end, you get the thread profile. Or circular, they also like gear. They rotating and approaching, and finally, you obtain thread in the workpiece. So either flat die or circular die. This is a circular die. Here you put like gear. It's very similar to the gear. Then this is a flat die. This is circular die. Then you can obtain the gear. Actually, let me tell you, this is a production, the mass production method. This is a mass production method to manufacturing thread. Let me show you the video. Just give me a second. Yes. Not yet. Okay, it's come now. You can see that. So it is here. This is one. So you see, initially it is blank. Blank mean is a new, right? So you see that it is thread profile is creating here. This is a blank, you see, blank. Blank mean new. And now this is a stopper, and this is a two rotating, this is a roller, two rotating roller, and we create a thread profile in the roller. So this one is a workpiece, is a blank. Then you see how fast it is? Fast and short. Then you get total, then you get a new blank here, very fast. This is a way actually to manufacturing thread in the, they are approaching, they are rotating and approaching. So they are rotating and approaching, as you can see, right? Okay, so as I told you, it could be either circular roller or rotating rollers, rotating two roller die, this is like this, or flat die. Flat die is creating also thread profile. Either this one or that one, we creating the thread profile. This is a mass production way. Also, thread profile can be done by using machining. By using machining, I think we did that, or we discussed that in chapter 17, 18, and 19 in machining. If you remember, we use a turning actually. We use a turning operation to create the thread profile. So thread profile could be done either by machining. By machining, we can create thread profile, or same thread profile can be done by using rolling process. So rolling and machining. So what is the best? Which one is better? Actually, let me tell you something. Let me tell you something. Please give me your attention. The most advantages, or the biggest advantages of the rolling over machining is the time. In the rolling, very fast, as you can see, very fast the process in the rolling, and this is a production rate. In machining, slow process. It takes time. It takes time to do the rolling in machining. This is the biggest advantages. However, there are some other things. Not only that, but what else? You can see that this is the machining, this is the rolling. What is the difference? Can you realize the difference? This is the machining, this is the rolling. What is the difference? You can see here in the machining, we cut the grain. Here we come here to machining because we remove the material, they cut the grain here. Can you see that? There are a discontinuity between the grain. The grain come here and cut. And there are a discontinuity. But in the rolling process, no cut. But what happened deforming? We push, we apply force to deform the material here. Then a grains here will flow around. Then there are a continuity. Grain are continuous actually, not cut, as we can see here in a machining. What does that mean? There are many meaning here. This means that if grain cut, this one could be lead to micro cracks, and there are some defect happen due to this one. However, here material is continuous. This one, another one, strain hardening. Material here exposure to strain hardening, and harder material means the harder surface can be produced by using the rolling operation. So you can see this sound great. So it means that, I mean, the rolling process is better than machining. Actually, it is, but still machining is better from the other point of view, which is what? Which is geometrical accuracy. The highest precision and accuracy can be done by using machining, because this is metal forming. Because you have to flow the material, you need to get smaller diameter, and then when you flow, material will flow and finally get the exact dimension. Actually, it is very difficult to adjust exact dimension. This is the always problem facing the deformation by using the rolling process, right? Next is the rotary tube piercing, which is also related to rolling process. What is the rotary tube piercing? Actually, rotary tube piercing is a hot working metal forming process to produce thick walled seamless tube. This thick wall seamless meaning tube, hollow tube. This is a hollow tube. Can you see that? It is a hollow tube, thick hollow tube. It is hot working process. So how we manufacturing this one? It is a solid, and then we create a hole. Someone has said that, okay, we do drilling. We get a solid material, we get a solid tube, solid bar, and then we do drilling. It's very difficult because this one is long. Then drilling process here will not accurately visible in manufacturing this kind of seamless tube. So how to do? Something like drilling, very similar to drilling, but in different way. In rolling, we do something very similar to the drilling, but we're not using drilling tab or drilling tool, but we use something else. I will show you. Initially, this is what we're going to do. This is a two roller, and these two roller are, as you can see here, have whatever we call convex shape. This is a two roller, and this two roller have two convex shape, and they have two different planes. This one have one plane, this one have one rotational plane. This is one rotational plane. The other one have different rotational plane, as you can see, and they are rotating. When you put the workpiece material, this is a front view, this is plan view. Whenever you put a workpiece material start rotating and feed. Whenever workpiece material come here, this is the steps. This is the initial step. Workpiece material comes. Second step, when workpiece material feed inside, then material will start to feed in this direction because of they have this kind of taper and convex shape and are rotating in different planes. And when workpiece material come inside, workpiece material start to feeding in this direction, move in this direction. Then we put whatever we call mandrel. This is a mandrel. We put the mandrel. So mandrel here initially, this is mandrel. Then mandrel will feed inside because material move in this direction. The mandrel is stationary here against the direction. The mandrel will penetrate and create hole inside. This is hot working, as I told you. Hot working initially when workpiece, this is the workpiece, when workpiece feed inside, this is whatever material workpiece is subject to tensile stress in the opposite direction. Whenever you have pressure here, then other direction have tensile. Material will deform because actually material will have like this. Material will have like this. Can you see that?
No, Doctor.
Yeah, because when you apply pressure, material will deform laterally. Then material will be subject to tensile stress in the other direction. We call it is a secondary tensile stress. This secondary tensile stress make an opening, small opening here. This small opening this small opening will be the initial hole here. Can you see that? When material feed inside, it will be subject to tensile stress in the secondary tensile stress, make a little opening, and then when workpiece feed in this direction, the mandrel will feed in opposite direction to penetrate inside to create a hole like this one. So this is a hole, whatever we call the rotary piercing tube. So this is related to the rolling process. Any question? Is it clear? So this is this is the rotary piercing process. Next is roll forging operation. Roll forging operation word, whenever you hear that roll forging, what you can understand whenever you hear roll forging, what you can understand? You can understand it is rolling and forging together. It is mixed between whatever we call rolling process and forging process. So it is mixed between rolling and forging process. What that mean? Rolling here, reducing the cross section, and the forging here, this is a part of forging to deform the shaping or shaping as hammering workpiece, hammering here. So here, because of we have this kind of deformation, we're hammering the workpiece together. So it is rolling and forging accent because they call roll forging. Some example, you can see that creating here shape, it's like hammering the roll move, and then this part like hammering the workpiece, like very similar to the forging operation. Since some part of the roller is deformed to shape the workpiece like forging operation, so they call it is mix between rolling and forging. They call it the roll forging process. This actually is the end of rolling operation. This is the end of rolling operation. Next section is the next part in bulk metal deformation, which is a forging operation. When I said forging operation, here we meaning that we're hammering the workpiece material. We're hammering the workpiece material. So forging operation here, as you can see, it's like a die. We have upper die and lower die. This is the workpiece material. We put the workpiece material inside. We're hammering the workpiece, and finally workpiece will deform. Workpiece will deform. Initially, you start with certain shape, and finally you obtain a material, as you can see here, with a different shape or desired shape at the end of the hammering or end of the shaping process. We have actually category in a forging operation. We have open die forging, impression die forging, and closed die forging. These three category in the forging operation. Let me discuss. Start first with the open die forging. Open die, we call it upset. Same meaning. Whenever you find that the word upset, it's same meaning like open die. And this one, compression, as you can see here, compression between the two flat die. This is one flat die, another flat die. We're hammering the material between two flat die, as one flat die, another flat die. So this one, we call it is the open die forging, right? This is the upper, this is the lower, and this is a workpiece. Ideally, if no friction, because here, as you can see here, the die is coming, hammering the workpiece or apply pressure on the workpiece, then what will happen? Please give me your attention, guys. Please give me your attention. So what will happen? The height will be reduced. The volume is constant. You agree with me? You start with certain volume, you end with the same volume. Volume is constant. So what will happen? Heights will be reduced. So how to compensate? You compensate the diameter. Diameter is getting bigger. So diameter is getting bigger and the height is getting smaller, but finally the volume is constant. Ideally, material will deform. Ideally, material will deform like this. I mean, you start like this, you get deformation like this. If we consider no friction here and here, and upper and lower end, the upper end and lower end of the workpiece, if we ignore the friction happening, then material will deform ideally. Then strain will be ln HO divided by H. HO initial height This is the H1 or final height. This is the H1. This is H2 at the end. It depends. Strain here, HO divided by H1. Strain here, HO divided by H2. It depends on the stage. So every stage. So strain change actually. When you reduce the height and you reduce more, then different strain. The strain rate equal to V divided by H1 at every stage. So here, for example, this is the V divided by H1. If you talk about here, this is the V divided by H2. Also strain, if you talk about here, HO divided by H1. If you talk about here, HO divided by H2. It depends on the case. So case by case. This is ideal deformation. In ideal deformation, you can see that sigma here, stress here is the Y flow. You agree with me? You apply stress to flow material. You apply stress to flow the material. Then Y flow is the stress you apply. What is the flow stress? Flow stress is the stress to flow the material. So actually, stress applied here is a flow stress. Whenever you reach, so flow stress is not constant. Then you increase. Whenever strain increase, flow stress increase. Whenever strain increase, flow stress increase. So here you start with the low flow stress. When you reach a certain strain, flow stress will higher. If you do more strain or increase the strain, then flow stress will be higher. So flow stress is different from case to case. Flow stress equal to K epsilon N or C epsilon dot M. K epsilon N in cold working. In case of you talk about cold working, flow stress equation is fine. But in case of warm working or hot working, C epsilon dot M. Then you need to change to C epsilon dot M. Epsilon here, ln HO divided by H1. Also epsilon dot equal to V divided by H1. Then force equal to what? Force here equal to Y flow multiplied by the area. Pressure or stress multiplied by the area. Then Y flow multiplied by the area. What area and what Y flow? Y flow at the point. So if you talk about force at this level, then Y flow corresponding to this strain of H1, and the area is the area here. Amani, you said area different? Yes, area different. You can see that. Diameter here is smaller. Diameter here is bigger. Diameter here is much bigger. Then you need to get the diameter. Every case, you need to get the corresponding diameter. How to get the question? How to get the corresponding diameter? Actually, volume is constant. Mean AO, this is the AO, that's what we know. AO, equal to A1, H1, equal to A2, H2. Then if you know AO, and you know H1, then you can get A1. Then A1 equal to AO divided by H1. This is the volume constant equation. Then you can get the A1 or the area at 1. Also same, you can get area at 2. Then you can get any area. Then you can see that you can get the force in every case, right? A Y bar flow is, this is the average flow stress, can be obtained as K epsilon N divided by N plus 1. This is the Y bar flow, exactly. This is the ideal behavior. This is the ideal behavior case. However, they said actually it is not like this. There are some difference. What is the difference? The difference is the friction here and here. There are a friction, and this friction, as we described, this friction actually limit the motion. Limit the motion here and here. Because there are a high friction, material cannot flow easily at the edge, upper and lower. However, in the middle, material can flow easily and more easily in the middle. Then you can see that material will be flow more in the middle, less in the edge. Then whatever we call barrel shape, we get whatever we call barrel shape. This barrel shape happen actually in a metal deformation. It's very common and very understood. So actually, this is not very good because this kind of produce is very localized stress inside, and this one also creating crack and non-homogeneous deformation and create crack inside. Actually, we would like to reduce. You cannot eliminate, but you can reduce. How to reduce? By using lubrication in cold working. Put oil in cold working to reduce the friction, or use thermal barrier, or use powder in hot working. Because we use that cold working, we use oil, but in hot working, probably oil is not very functionalized well. Then we use a powder, solid powder, use as a lubricant, or use ultrasonic to vibrate the blade to reduce the friction. Anyway, most important thing is to think about the way to reduce the barrel shape. As I told you, reduce, but you never can eliminate because friction is there. You're never able to make friction is zero, so friction is there. So you get, as I told you, non-homogeneous deformations. This one lead to a little bit inside crack, internal cracks. We need to reduce this kind of, as I described to you. How is this one affecting the force? Actually, initially, in ideal case, as we described, as we always do with a simple case and then move to the added whatever additional parameter. Then in an ideal case, y bar flow multiplied by area, or y flow multiplied by area. Y flow equal to k epsilon n or c epsilon dot m, and epsilon like this, and epsilon dot equal, as you know, v divided by h1. In case of in case of friction, added friction, then the equation little bit changed to become F equal to Kf Y flow multiplied by area. And Kf is this Kf, we call it, is a shape factor to added the effect of the friction. Then Kf equal to 1 plus 0.4 mu d divided by d. This is empirical equation. This one obtained by experiment to introduce the effect of the friction. As I told you, the difference between ideal case and actual is the friction. Then this Kf is additional part equal to 1 plus 0.4 mu d divided by it. This is we call it is the actual equation. And somehow it is an accurate equation to understand or to show or to calculate the force in the forging operation. Any question? Okay, let's take an example. Let's read together and try to understand. A cylindrical workpiece. This is a cylindrical workpiece. Let's read together. Cylindrical workpiece is subject to cold upset. Cold mean cold working, right? Cold not meaning room temperature. It could be up to 0.3 melting temperature. Less than 0.3 melting temperature we consider as a cold. Cold upset. Upset mean compression here, or this one, foraging process. Cold upset foraging operation starting 75. The height HO is 75, he told me, and the height 50, diameter is 50 millimeter, diameter DO, so diameter DO 50 and the height 75. It is reduced in operation to 36. Final HO become 36. I would like to tell you something. When you have a problem, try to make a sketch. It helps you to understand, right? In an exam, when you have a problem, try to make a sketch to help you to understand what is happening. The work material has flow curve K given and N given. This is a cold working, K and N given. Assume coefficient of friction is given 0.1. This is the mu. Determine the force at the beginning at 75, 62. Because this one starts 75 to 36, pass through several stages, 62, 49, and finally 36. So we need to obtain the force at 62, height 62, height 49, and the height 36. And also 75. I start first with 62 and come back again later to 75. Then I start with 62. I would like to obtain a case, the force in case H equal to 62. What is given? HO given, DO given, right? H here is 62, H here is 62, this is the first stage. K given, N given, mu given is a force. What is a force at 62? Then put the force equation. Put the force equation. Force equation equal to what? Force equation equal to K Y flow multiplied by the area. One by one, start one by one. K equal to what? K equal to 1 plus 0.4 mu d divided by H. I know mu, H I know, mu I know, given, which is 0.1, H I know, which is 62, but D I don't know. I don't know what is the diameter. Then to know the diameter, we must consider that constant area, constant volume equation. So as constant volume equation, volume can be obtained as HOD, area multiplied by HO, which is 75. This is HO. This is HO 75 multiplied by D divided by 4. By divided by 4 D square. Then you get the volume. This is a volume. This is a volume. This is a volume which is constant. I would like to obtain the D. I would like to obtain the D. Then area here, sorry, area here, and this one equal to the volume divided by 62, which is the height, because area multiplied by height, you get the volume here, then divided by 62, then you get the diameter. Then diameter can be obtained. Then we know the diameter, then we can apply here, we get KF. This is the first one. Second one, Y flow equal to K epsilon N. K we know, N we know, epsilon we don't know. Then epsilon equal to ln 75, which is HO divided by H, 62, then you get epsilon. Then you can apply, you get Y flow. Then you can apply here, then you can get the force. So force here can be obtained at 62. This is the force at 62. What about force at 49? Same. Then 49, in 49 you go to here, 49, then you need to obtain the area at the 49. Volume is constant. You get the area, you get the diameter, you calculate K. You calculate epsilon at 49 because it is ln 75 divided by 49. And then you can apply, you can obtain Y flow, and then you get the force at 49. What about 36? Also same. You apply 36 and you do same. What about 75? What about 75? 75 as a beginning. Then if you apply epsilon here, 75 divided by 75, meaning 1. Ln 1 gets 0. Then mean, this is very logic. 0 mean 0. At the beginning 0, because the strain is 0. No deformation. Strain, it's increasing with deformation. At 75, no deformation happens. Then strain equal to 0. Then force equal to 0. Because no force at 75, we don't have force. However, they said that we can a little bit increase. We can just consider strain equal to 0.002. Then by using strain, because it is 0, but we can just make it 0.002. Then we can calculate the force. The force at very little strain, just after 75, you can obtain the force in this case. This what is the solution. They said that at 75, 0, because at 75 here at the beginning, no strain and no deformation, and force equal to 0. At 62, this is the stage here. We calculate at 62, we calculate at 49, we calculate at 36. This is the last point. Deformation happened 75, reduced to 62, and then reduced to 49, and then reduced to 36. You can see that every time here at 62, strain become higher, and force and flow stress is getting bigger. At 49, strain is getting bigger. From 75 to 49, strain getting bigger. When you get a bigger strain, you get bigger force and bigger flow stress. When you come to 36, this is a maximum. At the last point, you get a maximum. At 36, this is the highest strain and flow stress and force also as well. If you do more deformation, you get more stress and more force. So you can see that force is increasing with the strain. Whenever you have a higher strain, you have a higher force and higher flow stress. Any question? Any question, guys? This one actually we obtained several times before. This is one determines the value of a strain hardening exponent. What is the value of N? Because it is always coming in a problem. What is the value of N if the average flow stress is 75% of the final flow? Average flow stress 75%. You put the equation, then you solve. Actually, this one done many times before. You put the equation. This is the Y bar flow. This is the Y flow. K epsilon N go. K epsilon N go with the K epsilon N here. Then you get one equation in N. Then you can obtain strain hardening exponent. Actually, it always happens like this. Didn't give you directly the value of N. This is another problem. It is very similar to what we just had before. Just simply solve it. It's very similar to what we had before, the same example. This is a different one. This is another problem. It's different. A cylindrical workpiece, 100 millimeter. Here, this 100 millimeter. 100 millimeter is diameter and 150 millimeter height. So HO and DO given, as you can see, HO and DO given. Is upset. Upset mean, as you can see, hammering. Hammering is foraging, open die foraging at 1200 degrees Celsius. This is hot. This is, please give me your attention. This is hot working at 1200 degrees Celsius, 200 millimeter. Means that final here is 100. You start with 150, final is 100. This is the hot working at 1200. Then immediately you expect that we're going to use the epsilon dot. We're not going to use epsilon, but epsilon dot. The Y flow equal to, then immediately, even without just move forward, then Y flow equal to C epsilon dot M and epsilon dot equal to V divided by H. Then you immediately have to realize as it hot or warm working. Material of the workpiece is a low carbon steel, graphite lubricant reduced. Graphite lubricant, they use a powder here. Graphene or graphite powder being used to lubricate. Oil cannot work here. A friction is 0.25, mu coefficient of friction 0.25. V here, speed of the press. Speed of the press is 2 meters per second. At 1200 degrees Celsius, material have parameter C and M. Then C and M as a constant are given. Determine what is the final diameter. What is the final diameter? D1. Then actually this one can be obtained from constant volume. You can calculate the volume, which is the AODO is the volume here. And then you have H1, then A1 H1 equal to AOHO. Then you can obtain the A1 and then you get the diameter of 1. This is the first question. Second, what is the true strain? What is the true strain? What is the true strain rate? True strain rate equal to minus V divided by H. Minus here meaning compression. The only meaning of minus here meaning it is a compression. So minus V divided by H1. V is given. Speed is given 2 meters per second divided by H1, which is height, which is 100 millimeter. This is the actual true strain rate. What is the flow stress? Flow stress equal to C epsilon dot M. Epsilon dot here and C and M given. What is the force? Equal to KF Y flow area. Y flow is given. Area we know. K, you can just, you have mu, then you can calculate Kf, then you can obtain what is a power. Power equal to FV, FV, this is the F, and V is given, then you can obtain the power required for the deformation process. Any question? Guys, any question? Is it clear? You understand? Okay, I will stop here. Time is finished. Next time I'll talk about several open die foraging operation. I will stop here. I will stop